think it is.
I'm going to turn it really loud. So you guys can go over yourself.
Good.
Try to make sure you know what you already said. So you don't
Right.
I'm helpful.
The first time. Yeah, it didn't really.
Something's happening.
Let's hear it.
Probably shouldn't be reading right now. That's second the extra.
So that first
Should be going. Because I'm live, it's broadcasting. It says I have 0 viewers, but it's I don't think so.
well, great. It's really we're there.
You see how it's so dark?
It's like scattering. Can you see?
Yeah.
How delayed is it? That's you guys.
Those are people in my computer.
All right, well, welcome everybody. Thank you for joining us for our very last set of presentations of the summer. And we're trialing, as you're probably all aware by now, because we have been playing with cameras up here, but we're trialing a test run of web-based presentations. So that's kind of exciting. Welcome to anybody who's joining us online. And test, we're trying to figure out what we need in video, etc. And I definitely welcome your feedback on how your experience online goes. So our first presenters today have been working with me this summer. Thad actually is returning. He worked with me last summer as well. And Alex joined us for the first time this summer. And we're looking at the electronic properties of materials that are used in solar cells. So I'll let them tell you all about their project.
Turn the volume down.
On this.
Good, like the live stream to the speaker.
Okay. All right. Well, thank you everyone for being here. We're very excited to present to you. So we're going to talk to you about solar cells and solar energy. It's stellar. Stars. All right. So why solar? As you may know, there's a global climate change going on, and we are increasingly needing more and more energy, and so we want to find renewable energy sources that aren't fossil fuel reliant. So big picture-wise, that's why solar. Here's a map of North Africa, and you can see those red boxes. Those red boxes inside of there, if you were to cover that with solar cells, that would be the area of land you would need to supply the world's energy needs, the European Union's energy needs, and then that's Germany right there. So in proportion to all of the land mass, it's not too much. Looking at the US, we actually only need about 0.4% of the total land to cover in solar cells and provide for our energy needs. That doesn't make a lot of sense. So let's take a look at Oregon. Those two counties right there, if you were to cover them in solar cells, that would be more than enough to provide all the energy for all of the US. So there you go, just a quick infographic to give you an idea of how much energy you would be able to get through it. Over the years, solar energy has been decreasing in costs. First started commercialization in the late 70s, and now it's about 30 cents per watt. So it's been going down. And part of the reason is due to increasing efficiencies of solar cells. So this is a big map. Those blue dots and the blue lines up there are a crystalline silicon solar cell, and that is efficient, but it also uses a lot of energy and it uses a lot of material because you have to melt the silicon, which takes up a lot of the wastes energy and heat. And then it's also really thick. So we're not focusing on those solar cells. The solar cells that we're looking at are called thin film solar cells. And the particular kind of solar cell we're looking at is a SIG solar cell. And part of the are so neat is because they're so thin, 6 micrometers. So it doesn't take a lot of material. So you waste less energy and you waste less material. You can also print them on something flexible like a plastic. So this is the SIG solar cell that we're looking at, copper, indium, gallium, selenide. And if you look on the right, that's an SEM image of the solar cell. So if your solar cell were a sandwich, you were going to cut into it, this is what it would look like. And you can see the SIG absorber there. Ours is about 2 micrometers, and it's got a molybdenum back contact, and it's on a glass substrate. But like I said, you can put it on plastic or something like that. You'll notice there are these white kind of lines here. SIG is a polycrystalline material, which can be bad in some instances because if you have little pockets where charge carriers can get caught into, that can lead to deficiencies in the cell. And one of the ways you can look at those deficiencies is through measurements such as capacitance, which is what we do. So we measure capacitance. It's a sensitive measurement. And what capacitance is, especially differential capacitance here, is a change in charge per a change in voltage. So you can look at the far right, you have this perfect crystal structure right here. But of course, you're going to have non-uniformity in the crystal. So that can look like a missing atom or stretched crystal lattice, anything like that, that makes it hard for the charge carriers just to fly through. That's going to show up as a deficiency. You lose energy that way. So by changing voltage, so an AC signal, your house runs on an AC voltage, you plug it into the wall. And depending upon the frequency, we can see different properties. So if we have a low frequency AC voltage, there's enough time for the chargers to respond to that voltage and jump in and out of these trap states, which is what happens with the defects. But if you increase the frequency, you don't have enough time for the charges to jump in and out of these trap states, so it doesn't show up as capacitance. So if they're jumping in and out, you get capacitance. If they don't have enough time, they freeze out. You don't see capacitance, which is what's happening here. We have the capacitance right here, and as we go to higher frequency, it drops down. And from this, we can determine trap energies and things like that. So here's a look at our setup. That big old orange ball right there, that's a helium balloon. So what we do is we have a cryostat and we fill it full of liquid nitrogen, super cold, and we need a good thermal insulator. So we pump the chamber with helium and then we cool our sample down. It's easier to look at the types of measurements that we want to look at when it's really cold. So that's why we do that. And then a bunch of electrical equipment. And then down here is our solar cell. See this little, really, really small. It's like a few millimeters in length. And that's the actual part of the solar cell that we're measuring. So then we just put that on a stick and we put it down in the cryostat and do our stuff. So Thad is going to talk to you about what exactly it is that we do in particular.
Okay, so the first measurement we do is admittance spectroscopy, and this is where we apply an AC voltage and then measure the AC current to then calculate capacitance. And what we're doing here is we're changing the frequency, kind of like Alex was talking about earlier. So that graph up in the right-hand corner is actually our data. And so you can see at the lower frequencies, we have more of these charges moving in and out the trap, so we have a higher capacitance. Then as we go to the larger frequencies, we have the charges are getting stuck in the trap, so we have a lower capacitance. And you can actually see a temperature dependence. So at higher temperatures, the sort of transition frequency where the capacitance starts to actually decrease is higher than at low temperatures. And this makes sense because, higher temperatures, there's more energy in the cell, and the charges can just move around a little bit easier. What we are really focused on is what this stepping capacitance actually tells us about the defects and what's going on. So there's a few possibilities. It could be majority carrier freeze out, but that's not too likely for our cell because that usually happens in SIGs at way higher frequencies. It could be the majority carrier trap state, and that's what we're talking about where the charges are getting stuck in the traps at the higher frequencies. It could be a defect at the interface, which is the top of the SIGs material in the cell, or it could be a defect that's a bad back contact. So we're really working on how do you determine or distinguish between these defects. So one measure we do is capacitance voltage. In here, we're still applying an AC voltage and measuring AC current to calculate the capacitance, that kind of stuff. We're also adding in a DC voltage that allows us to like look at different parts of the cell. So what you'd expect is as we go into forward bias, we see this kind of increase in capacitance, but you'd expect that to just keep on increasing. And what we actually see is a sort of rollover where the capacitance starts to decrease. So this is our actual measurement. And then up in the corner is our double diode model, which is like a model that would show a bad contact being there. So this graph is a graph of our model with a bad contact, and that kind of correlates to our data. So from this CV measurement, we do see a bad contact coming in. So we thought, you know, how can we actually distinguish between a bad contact being there and a defect in the bulk material? So we thought we should maybe like combine these two measurements. So this is emission spectroscopy with an added DC voltage. So here is the reverse bias where we're putting negative DC. And right around here, there's a transition. It's around like 7,000 hertz. You can't see it because it's not zoomed in, but I promise you it's there. And then as we move farther into forward bias, you can see this sort of shift to lower frequencies for the transition frequency. And you can see it better on the graph on the right because it goes from 0.6 to like 0.8, and that kind of stops right around 2,000 hertz. And what's interesting about the graph on the right is as you go more into forward bias, the total capacitance measurement at low frequencies sort of hits a peak at 0.8 volts, which is that teal line at the very top. And then as you go farther into forward bias, the total capacitance at low frequencies actually starts to decrease and even goes negative. So we are measuring negative capacity. We're sounding crazy, but people have actually measured it before. People have seen it in laser diodes, light emitting diodes, and even silicon solar cells. So what is going on here is that we are so far in forward bias, we're injecting a bunch of minority carriers, and so our like normal model is just totally broken down now because we are just so far in forward bias that we can't even rely on our model anymore. So going on with our analysis, what we do is we take the derivative of those previous graphs, which would then show us the fastest change in capacitance, and that's what these peaks are. So this is the reverse bias peaks that I told you about, and they're all relatively around 7,000 hertz right there. And then this is the forward bias peaks, and you can start to see at like 0.2, and then moving on, they shift towards the left to lower frequencies. And so what we do is we take each of these peak frequencies and then apply them on a linear plot. And then from the slope, we can then determine an energy level for this sort of defect that we would see there. And so 0.4 volts in reverse bias, that gives you 113 millielectron volts. Neutral gives you 100 millielectron volts, and then 0.8 volts in forward bias gives you 86 millielectron volts. So looking at this graph, this is the energy levels we determined for all the different DC voltages we applied. And if you look at this range, the -1 volt to -0.6 volts, you can see that the energy level is like relatively the same. And so what this tells us is that there isn't a defect at the interface, because an interface defect responds dramatically to a change in voltage. So since they're pretty much the same, in any case, there isn't an interface defect. And if you look at 0.2 to like 0.8 volts in forward bias, you can see that those are relatively the same level too, and they're actually below the energy level at 0 volts. So what this tells us is that we actually don't see a bad contact. Because if you see a bad contact, the energy level would be increasing as you go into forward bias and be above the level at 0 volts. So this graph tells us there isn't a defect at the interface, there isn't a defect at the bad contact. So what we're probably seeing is just a defect in the bulk material that just has different localized energies throughout the material. So our future work would be to determine the effect of negative capacitance on our actual measurements and maybe try and study more to see what it could tell us about the cell. Also to use other methods to determine the uniformity of our cell, like actually how thick the layers are, like if copper is moved over into molybdenum, or kind of like moving around, stuff like that. And we also want to make more repeatable data for different samples, like maybe look at cadmium telluride, which is another popular thing. So thank you, Dr. Jennifer Heath, and thank you, Faculty Student Collaborative Research Fund and the Physics Department.
Thank you all for being here.
Yeah, thank you for being here.
So how do you describe what negative capacity?
So 6 is a p-type, so the minority carries an electron, which has a negative charge. And so when you're so far in forward bias, the front bands are basically flat, and you're just injecting a bunch of electrons. And the current we measure is, protons. So we're injecting so many electrons, holes. And so we're injecting so many electrons that we're measuring current going backwards.
Interesting.
It's kind of wacky.
What's the source of your cells? How much do you know about them before you start your experiments?
We get them from Bill Schafferman at University of Delaware, so we know quite a bit about them.
And what kinds of things do you know?
Like
How they're made,
yeah,
what the thickness layers are.
and like the doping densities of the materials and stuff like that.
But there could be still some.
But this cell we're measuring is actually like 15 years old. Yeah. So some things can happen after change in time. I mean, it's even amazing that we're actually getting measurements when it's this old of a sample. So.
So you said that you ruled out
The interface.
the interface being the problem, so it's the bulk material. So what exactly, can you do something to make it better?
I don't know, because those defects in the bulk material kind of come from the process of making it, because it's like a gallium atom is in the wrong spot, or there's like electrons missing and things like that. So it kind of just depends on the process of actually creating the cells.
There are way more efficient cells you can make too, that are just a bunch of different things. It's a polycrystalline material, so you're gonna get these interfaces and things. So it's not a perfect crystal, for sure. Yeah.
I'm going to read Alex's email. President's email.
So our next speaker is Grant Cates, who worked with me this broad new project, fly swarms and complexity.
Okay, so like Dr. Murray said, fly swarms and complexity this summer with hopes of being able to model them or model that computationally. So what is complexity? Super tiny. We have this nice video. So complex systems are abundant throughout nature. And one of the most common experiences is that of a flock of birds. And as you can see, these systems exhibit some type of collective intelligence behavior. They seem to move as one unit rather than individual particles. Now, this behavior is notoriously difficult to quantify and model, but we're attempting to do just that. Okay, exactly. Specifically, it's the study of the phenomena which emerge from a collection of interacting objects. You can think of it as a system that is internally driven to some characteristic state. Sometimes it's also called a scaled. We're looking for unexpected order in seemingly complex systems. And one of the lens for analysis is through self-organized systems. Get really excited and skip over stuff. Okay, so this is what we're doing. So before we can understand why we want to study them, we need to understand what they are. Bach and his colleagues posited in their original paper in '87 that dynamical systems with extended spatial degrees of freedom naturally evolve into a self-organized state. This is where we say the system is internally driven towards a critical point or some state. You can also think of this as a phase transition in the system. The objects go from acting as individual objects to a cohesive group. That's the dynamics at that point. And the classic example given is out of a sand pile, a nice sand pile right here. We are adding 1 grain of sand to the center of the pile at a time. At some point, the slope of this pile is going to exceed a critical threshold, and an avalanche will occur to relax the pile. Now, sometimes the avalanche is small, and sometimes the avalanche spans the entire size of the pile. The hallmark of the SOC system is that there's no characteristic time scale or size for these avalanches. And that essentially means that it's impossible to predict how a perturbation will propagate throughout the system. And SOC analysis has already been applied to many fields, most of them outside of physics, even though I would argue all science is physics, but that's neither here nor there. But some of the most recent ones are earthquakes, forest fires, and neuronal activity. It's also been used to study the formation of galaxies, analyze stock market trends, and in the past, Dr. Murray's done research on applying SOC analysis to protein folding as well. Now, there are some valid criticisms of SOC systems that I think are worth mentioning. The first is the fact that some people claim that this is not a science. And they claim it's not a science because it provides false models. And a false model, a system is called a false model if it doesn't describe what's happening beneath the surface, rather it just makes predictions of outcomes that will occur. And there's a really great paper written by Roman Friggs that sort of analyzes the philosophy of this type of analysis. And Roman Friggs points out the criticism that it's more so a mathematical skeleton that scientists are picking up and applying to use and then reappropriating the definitions of like an avalanche or a sand pile. But SOC provides us, so we ignore these criticisms. So admittedly, when you hear that people are studying earthquakes and galaxy formations, fly swarms don't seem like the most exciting system to study. Fly swarms. But there are good reasons to study fly swarms. First, I chose to study fly swarms, and she's lost study. But more importantly, these are simple, complex. And I say they're simple, complex systems. Complex in the sense that there are a lot of moving parts. But it's simple in the sense that the mechanics that this move is actually simple. Start with the basics and master those before you move on. And that's exactly what we're doing here. And fly swarms are also a popular troves of data on flies. We have something to compare our results to. If our model makes a prediction or unexpected, the scientific community is ready to confirm or refute that. Fly swarms are actually a current topic of research. Up until recently, we could only track systems that were moving 2-dimensionally or track only a few individuals moving in 3 dimensions. But now, with greater technology, larger dimensions. And one group that did just that published their findings recently in the PLOS Computational Biology Journal. It's a really short video because you had to pay to convert the full thing. And but you can sort of see this collective behavior. These are midgets. You can see they're moving in this cohesive sense. And here's a picture of one of the swarms. But the group was trying to determine, and I quote, if correlation is amplified by the vicinity, to some critical point in the parameter space. And what they found is that these fly swarms actually do fine-tune their parameters to maintain the scalability of the correlation function. So we have some experimental data. Before we do that, I want to go over why I think this is interesting, because it's really important to find personal interest in a project, especially if you're going to be spending hours in solitude going over it. First off, as a theoretical physicist, models are your bread and butter. So being able to produce models is paramount. Now, Dr. Murray teaches a really great computational physics course. I think it's only offered in the spring. But she does a really good job of introducing students to the math and sort of how to think like a programmer. I really recommend everybody who's interested in going in the STEM fields taking this class, and you need these skills to build on that foundation of skills. But what really got me to commit to wanting to work on this project was Dr. Murray's description of taking systems that are seemingly complex and finding the simple rules or patterns that govern those systems. Because at the heart of it, that's what physics and science truly is. And then there's the theory of everything, which many of you will know is sort of like my holy grail. And there are people that throw SOC systems around with theory of everything. And while I don't think that studying these systems will lead to a theory of everything, it's definitely a step in the right direction because we're trying to analyze complex systems. Even though some people claim they're false models, in that philosophy paper I was talking about, I think said it best when he said false models and theories can be a vehicle for successful research and eventually lead to an increase in knowledge. The most exciting thing is the fact that it's a new area of research, which means if we find something out, it will be the first time that anybody's seen it. So we've been doing computational research. Computational research is a lot like experimental research. It doesn't care. Model. Find an experiment. This can be the most frustrating part, especially if you have no idea what you're doing. But the best way to do it is to distill your system down to its most basic form. And once you get that down, you can slowly add in more complicated features until it resembles the system you're trying to model. And then you want to test the model. This step is really, really, really important. You have to ask yourself, do these answers make sense? You can't just accept whatever your model plops out and say, okay, this is true. I know this is true. You have to be skeptical. And then you have to decide why you think these results make sense. And then you have to, well, interpret the results. Once you've tested the model, you get your results, and you ask yourself again, does this make sense? Is this what I expected to happen? Why did I expect this, or why did I not? We'll ask ourselves those questions a lot. Okay, so let's build our model. Like we said, the first step is to simplify the model. For us, this meant taking a square lattice and randomly generating flies on this lattice and moving more complicated features. So the first step is to generate the initial positions. So what we did is we took a square lattice and we determined how many lattice points we have. Here we have 9 lattices. We then generate a string going from 1 up to the total. Now, these numbers correspond to Cartesian points. 1 is 0, 0, 2 is 0, 1, or 1, 0, 3 is 2, 0. We never use these. Whatever. Okay, so then we decide how many flies we want. Let's say we want 4 flies. We're randomly going to select 4 numbers from this list, and then we're going to translate that back into the Cartesian points, and now we have our initial positions. And so the next step is to generate rules to move the flies. Now, moving flies is where it's a big computational problem. If you remember from that video or your history, these fly swarms or flocks of birds move continuously and instantaneously in the sense that all of the objects seem to move at the same time. We can't mimic this behavior computationally because we have to move the flies individually. So how do we try to capture that behavior? Well, we decided that for each time step, we would move the flies in a random order. So at the start of each time step, a fly is selected at random, it randomly chooses the position to move, And then that process is repeated till all the flies move. Now there are two, or at least two issues with this type of model that should just be jumping out at you. I'm wondering if anybody has an idea of what those might be.
It's two-dimensional.
Okay, that's more of a simplification than problem. But let's watch this again. Now, imagine, think we're trying to model a real-life system. So what's happening here? Usually be an issue. Two flies go into the same place, and one goes off the lattice. And these are really important questions because in real life, two objects cannot occupy the same space. And then if a fly flies off the lattice, well, what does that mean for our model? Well, we don't care yet, but those are really important questions or concerns to realize. Remember, we're still trying to build this. Yes, yeah. So here's an example of one of our preliminary models. Now, to make this a video, I had to employ some type of boundary condition. So I added what I call the Pac-Man boundary condition. So as a fly travels off to the right, it reappears on, it goes up the top, and it comes back on the bottom. So we'll take a look at this. Mainly, we're trying to test to see, does our model behave the way that we expect? And when I got this work for the first time, I was really, but I was excited mainly because I was like, oh my gosh, it looks like there's this noise for movement. And I was really excited because I just have simple rules and we already have this unique behavior emerging. I go tell Dr. Murray and I'm all excited. I'm like, look at this. And she goes, okay, well, we need to test it. And I was like, but it's right there. And she said, you need to look at it and see what's going on. So I look back over our code and it turns out that there was a select programmed in that I had to rectify before we could move on with our simulations. So we got that fixed. We got our flies moving in a way that somewhat makes sense in nature, but we need to figure out how our system. And this brought up a whole new slew of questions. Like the big one, how do we define a swarm? And then how do we recognize a swarm within our model? It's kind of hard to study swarms if you don't know what they are. And in lieu of having a working definition, how do we continue on with our research? Well, we think that the swarming behavior has something to do with the density of flies and the interactions between them. So we're going to focus on those two objects or those two topics and then hope that in the future a more cohesive definition will sort of present itself. Now, a really common tool used in computation is that of a random walk is exactly what it sounds like. You have some object and each time step in a random direction. Now, to average what's called the RMS distance or the root mean square distance, current position to its initial position. And then if you take that, we can use it as a baseline for comparison with our model. And we can also use it as an extra layer of testing to ensure that our model is working properly. We have a scenario where we know the outcome, we test it against our model to make sure that our model is working properly. Of what we should expect. It's 100 flies moving 100 steps, and then that's one iteration, and then we average over 100 iterations. Now, each one of these black dots, I promise they're dots, represents one iteration, and it's the average RMS distance for each fly at that point. And when you average them all together, you get this nice straight line. So that's what we're looking for. So we ran our model for 100 to 1,000 flies. And each fly has 100 steps, and we did it for 1,000 iterations. And here is up to 400 flies. You can see, or rather you can't see a difference between the data and the best fit line, which suggests that our data fits our best fit line really well. This slope for each one of these graphs is essentially 1 to 2 decimal places. Now, we have to ask ourselves, do these results make sense? Are these what we expected? Well, since our model is essentially a bunch of random walks, this is exactly what we would expect. So we can say, okay, our model is functioning properly. Now let's try to add in more sophisticated rules for movement. So the first thing that we decided to focus on was we can also arrive at these results analytically. And when you do so, it yields this equation, which is the average R-squared value equals 2dt. T is our independent variable, it's time, and D is the diffusion coefficient, which for this case is 0.5. And when you have one at 0.5, it represents uninhibited diffusion by random walk. Okay. So now that we have our baseline data, we can add in our nearest neighbor avoidance. This we thought was the most important because it's a pretty fundamental law of nature that two objects can't occupy the same space. So it seemed like a good place to start. Now the way that we do this is instead of letting the flies move anywhere, we limit their potential moves to unoccupied spots. Now notice we still don't care what's happening at the boundary condition. That's still a problem for a later day. The protocol for doing this is actually quite simple. At the start of each time step, we're going to generate a list of all of the occupied spots. Then from that list, we're going to randomly select a fly because each row is a different fly. And that's the fly that we're going to move. We know it can move north, south, east, or west, so we determine all of the possible moves. And we compare that list of moves back with our list of occupied spots and remove any duplicate entries from our possible moves list. And then from that remaining list, we randomly select a move to perform. If there are no moves left, then the fly will stay stationary. And this process is repeated until all the flies have moved for all of the desired time steps. So each of the following graphs are going to have two data sets. The top one is the nearest neighbor avoidance data set, and the bottom one is that baseline data that we've already seen. Now, as you can see, the slope for all of the nearest neighbor avoidance is actually greater than the pure random walk. And it's all significant, or it's all measurably above 1. So what does this tell us? This suggests that the flies are moving away from their initial position at a faster rate. So then our next step is, do these results make sense? Well, if you think of the flies in the initial positions as concentric rings of flies, the outer ring is going to move away from the group. That's really the only option that they have. As that ring moves away, the second ring now is free to move away. As that second ring moves away, it's blocking or inhibiting that first ring from turning around and retreating. So as this process is carried out, the net result is that the flies are moving away from their initial position at a faster rate. So what do the results that we have thus far tell us? Well, first, we added in a new feature, and we can tell that the new feature caused a non-trivial change in results. We can also say that the new results make sense because we can sort of explain them away intuitively. And the new results are that the flies essentially flee faster. That's really hard to say, flies flee faster. Practice that a lot this morning. Now, we can also think of the nearest neighbor avoidance as a weak repulsion force that's sort of pushing these objects away from each other. And so if we hope to have any type of swarming behavior, we need some type of attraction force to counterbalance that. And this is mainly what we're working on right now. So there are many items on our to-do list moving forward. To name a few, I'd like to streamline the move selection. When we started doing the nearest neighbor avoidance, it got really computationally expensive to check which spots are occupied. And so I'd like to turn it into a Boolean process to sort of speed that up. But I have no idea how to do that. So that'll probably take me a while. And then we'd like to incorporate realistic flight behavior and interaction between flies. We have sort of started studying fly behavior, which means I've been reading a lot of biology journals, which is slow going for me because there's a lot of words I don't know what they mean. But I have been able to figure out that flies normally fly forward, left, or right. They don't normally retreat. There are certain behaviors that certain flies will follow. So we're going to try to incorporate those in the future and also put in this correlation between the flies. And then we'd like to get a working definition of what a swarm is so we can sort of move forward with our research and actually study the swarms and look for these SOCs. We like to see how these swarms actually form, how large they can get for different parameter spaces, and how they dissipate and at what rate. I would like to thank Dr. Murray for being my research Sherpa this summer. I'd also like to thank Linfield College Faculty Student Collaborative Research Fund for paying me, not making me get a real job this summer. Linfield College Physics Department, they're very supportive. It's the best department here. Everybody should switch their major to physics. And I would like to thank the members of StackOverflow.com. If you're ever trying to figure out how to do something in MATLAB, this website will save your life. And for all of our friends watching on the internet, don't come after me. All these images and videos are public domain or common license. And I will now take questions from the audience. No questions on slides? Oh, yes.
First, I would argue that doing research over the summer should qualify as a real job. So, let's keep that in mind. Secondly, what about this? Do you think that if you find some model that applies to flies, do you think you'll be able to apply it also to birds or to fish? Or is there something particularly fly-like that you think you'll find in this model?
I don't think we would be able to like cut and paste the model to apply them to birds or fish, for instance. If you look at the different ways that those systems behave, there's more chaos in like a fly swarm compared to a flock of birds, whereas they tend to move in a uniform direction and more so as a cohesive unit. But I think applying it to fly swarms will teach us how to apply it to different systems and give us a good starting point to apply it to those systems. And like I said, starting with a simpler complex system, we can figure out what we can learn, if anything, from this type of analysis before we move on to more complex systems.
You mentioned that like the go-to example of these kind of models is like sand, right?
Mm-hmm.
And then people have been like redefining things like sand and avalanche to
Right.
suit their purposes. But then you start talking about flies, and to me that seems like a big jump to something that's alive versus grains of sand. And I'm just wondering how successful these models have been in modeling the behavior of something that's alive.
Well, there has been experimental data collected that has sort of been able to show that the scaling of this correlation function, which sort of determines how the other flies influence the individual flies' move choices, behaves, and it follows this power law distribution, which is sort of the hallmark of the SOC system. So that's sort of the flag that's saying, hey, look at me, we think that there's something important going on here. That group, I like to think of it as sort of approach opposite sides. That group was observing the system and determining if this certain characteristic is there. And we're starting from basically the ground up and trying to build in the different behaviors that lead to that system. So we can say, you know, we didn't have fly swarmings when we added the nearest neighbor avoidance, but when we added this correlation function, we got this collective behavior. So we think it's the correlation function that's leading to the SOCs.
I'm just wondering how well the behaviors of individual live beings can be modeled with a function.
Well, and that's,
Like,
when Dr. Murray said fly swarms, that was the first thing I thought of. So I was like, this is a biological system. There's so many things in a biological system that you can't quantify because we say that things have free will. And so how does that affect your model? But the fact that we have seen this behavior, to me, is interesting because it suggests that there are conditions that are imposed upon these flies that sort of override any free will that they might have. And it's interesting to see how that might apply to more complicated organisms like pack animals or other types of organisms that exhibit this behavior.
So when I'm thinking of like a pile of sand or pile of gravel, I can like understand the criticality of say like when it has like an avalanche or something. But but I'm sort of having a hard time like visualizing or wrapping my head around like what is the criticality of like a line of swarms? What is critical behavior?
The critical behavior would be the swarm, or that's what we are tentatively defining as the critical point. The critical point, I think it's easiest when you think of it as a phase transition. It's the point where the individual flies are not acting as individual flies, they're acting as a cohesive unit. So that would be the critical point or the critical threshold that we're looking for.
Do you think that there's going to be like a distinct line where that criticality happens, or is it going to be just this sort of, because I can see it being like, you know, a couple more flies here, a couple more flies there, now they're kind of behaving as a group. It's not going to be like this sharp.
Well, that's what makes this really difficult, is that there are so many different parameters, and especially since you're doing it in a computer, you can give these parameters any type of value. And while I would like to think that there's a distinct point where we go from non-organized collective behavior to organized collective behavior, I don't think it's going to be a solid line. It's probably going to be something where we start to see some type of correlation, and then once we do that, we've sort of fine-tuned the different parameters, holding the others as controls until we can reproduce these fly swarms.
It seems exciting that you were able to figure out that that selection bias had been programmed in and then go back and find that. Can you talk a little bit about how you did that?
I spent a lot of time this summer staring at my laptop, staring at MATLAB. Luckily, one of the things Dr. Murray taught us in her computational physics course is to comment the crap out of your code. That way, when you go back and look at it, you can remember what this line of code is supposed to be doing. I found out that when I was cycling through the different potential moves, and I was removing them, you have to do that with a loop. And I was doing it with a for loop that basically says, we're gonna do this iteration 4 times. And on the first iteration, we look at the first element. The second iteration, we look at the second element. Well, and so on. And so if the first iteration, we're looking at the first move, and I remove that move because I say, no, we can't go there, and then it deletes it, it actually moves up the other 3 moves. So move 2 is now move 1. And so that creates an issue when trying to go and select the move. So it turned out that more often than not, the move that was left over was the north move or the east move for the way that it was choosing.
How did you correct that?
So I used a temporary array, and before deleting the move, I marked or flagged the move as not a number, which is sort of a marker that you can use in MATLAB as like a null field. And then after moving through all of the potential moves, I found all of the rows that contained a not a number element and removed all those rows at one time. So therefore it was like a one-step process versus that moving through.
Sorry, more questions. So you were talking about defining the word swarm.
Yes.
Or swarm as a collective system. So why is that important? Is it defining it for you, for your like research, and you and Dr. Marie, or is it for something?
Well, as humans, it's much easier for us to study and hold things in our mind when we put a name to them. But it also helps to put something to that name. So to say we're studying fly swarms and we're trying to model fly swarms, on the surface that sounds pretty black and white. We all have an idea of what fly swarms are. But when you're doing it computationally, you don't have those same indicators as to what a swarm is. And so you have to come up with an explicit definition of when we've crossed that line from having a swarm, or from not having a swarm to having a swarm. And we just haven't, we're not at a point in our research yet where we can make that distinction.
Will you come to a point where you're looking at actual living fly swarms and comparing what you've done to what you're seeing? I mean, I know you've had some videos from previous research, but.
Personally, I hope not. Fly, it's not my cup of tea. And experimental work is also not my favorite thing. I really like the theoretical work, but that's the great thing about science is that we can do the computational work, and then some biologist who loves flies can take our models, and try to reproduce our results. So.
In your model, you assume that each fly they move at the same speed,
right?
And they go during movement. And from the video, seems like the whole thing they have different densities.
Yes.
So I wondered, like intuitively, I would think when there's greater density, they will have less freedom to move, so they may move slower than the flies that are outside. Right. I wonder from the biological papers you have studied, is there any evidence to support?
There's, and I'm gonna try to regurgitate this information because it's very math heavy and it's still a little beyond my scope. But there have been studies that find that the average velocity of all of these flies that have this correlated movement is constant or equal. So moving them essentially at the same speed, which is 1 unit per unit, or 1 unit length per unit time, is sort of a way that we can try to plug in that behavior. But also a more truthful answer is that it's easier to do this now than it is to try to do something more complicated like that. Like also, the flies don't necessarily, if they're more densely packed, they're not necessarily going to make the same unit length step each time. That's probably going to differ as well. And we might get to a point where we move the flies a random step size versus like a unity step size. But that's so far from where our model currently is that I don't want to worry about that.
Yeah. All right, I'd like to thank Thad and Alex and Grant for bravely participating in our first webcast, and thanks to everyone joining us online. Let's give them a round of applause.